All right, in this little video lecture, we're going to look at a couple of different ways of counting the number of set bits in this case, an unsigned integer. And we'll look at an obvious algorithm, and then we'll look at an algorithm that is perhaps not so obvious. And we'll put this to use when we implement our bit set. So first of all, if you have an unsigned integer and you want to just count the number of bits, in this case we want the number of bits to be 4, our output. We can do this using the bitwise the bitwise operators that we talked about in the previous lecture. And so one thing we could do is so here's our number n, and then we have our mask, and I could start with 1 in the first position, and if I AND these two together using the bitwise AND operation, then I get 1, and then if I shift the bit over and I do this again, I get 0, and I keep shifting along. And so what I can do is, by using AND, I get an expression that's true every time I encounter a bit on the number. So what you can do is you can start off with a counter at 0. How many bits do I have in my number? Well, I can use, and I'm just going to use capacity because that's the total number of bits that I could have. So I'm just going to call that capacity. And I know how big my number is because that tells me how many bytes it is, and then for each byte we have 8 bits, so that will tell me how many iterations I need to make. And then I've got my mask. And so now I can just loop up to capacity. And then every time, and then I'm going to check, and every time it's true, let me move this up a little bit. If I AND my mask with the number, and if that's true, then I can increase my count. And then I have to shift my bit over 1. Just like that. And then finally I can just return C with the count in it. And so if we were to put this into a function, I would be returning an unsigned, and let's just call this count bits. And then I would pass in this unsigned value here. And then that gives me my counting. A slightly less intuitive thing, and here's kind of the insight, is okay, so just going back to here, this actually loops for each bit, right? Loops for each bit. Okay. But there's a better algorithm that only loops for the number of bits set in the number, okay? And we can either call this Wegner's algorithm, and it's also known as Kernighan's algorithm. For counting bits. And, you know, just the history on this, Wegner actually published this in the Communications of the ACM back in 1960. But then an implementation of the algorithm appeared in Kernighan and Ritchie's C programming language book. And so that's how Kernighan often gets the credit. And then it was also independently rediscovered, independently discovered by Derek Lemire, and that was published in 1964. So anyway, so what we're going to do here is we're going to loop for each bit. And the way that we can do that is by using the AND operation. And so we're going to start with count. And I'm going to loop. And what I'm going to do is I'm going to modify n, and eventually n will become 0, and that's the termination condition. And every time I loop, I'm going to increment my count. And I can simply compute the AND of n with n minus 1. And then I can just return C. And then if I bake this into a function, and then I need to put a little semicolon right here that I forgot. And I could have also removed this expression since I initialize C above. But I'll let you make those changes. So I'm not going to do an exhaustive code trace because it's just too many bits to have to write. And but I do want to just give you some insight into why this method loops for the number of set bits as opposed to the number of bits in the number. All right, so let's look at a simple example with 8. So if our number is 8, and in binary, that's 1000. And if we subtract 1, we get 7. And of course, that is that in binary. And by subtracting 1, we're guaranteeing that we get a bit mismatch at a particular location because we're subtracting 1. And now when we AND this together, we get 0. And so any time for any number you can think of that has 1 bit, if you subtract 1 from it and AND those two numbers together, you're always going to get 0. Another example is if we have 2, which is 1 and 0, and we subtract 1, we get 1. And again, we're kind of guaranteeing that we have a mismatch where there is a bit. And we AND these two together, then you end up getting 0. If we take another example, how about 9? So if I have 9, which is 1001, and I subtract 1 from it, I get 8. Again, I guarantee that I get a bit mismatch one position. And now when I AND these two together, I get back 8. Subtract 1. Now I get a bit mismatch here, and all these others are 0. And when I AND these two together, I get 0. So that's the intuition behind why this algorithm, Wegner's algorithm, or also known as Kernighan's algorithm, why this little expression here works, and then why this loops for the number of set bits. And we're going to put this to use when we implement a bit set.